So far we've been talking about just individual gases, but a lot of times gas samples are mixtures of more than one gas. If we think about air, air contains a lot of different gases in it. What we call dry air contains nitrogen, oxygen, argon, carbon dioxide, and a few other gases in trace amounts. By dry air, we mean that it doesn't have humidity in it. It doesn't have gaseous water in it. So the air is 78% nitrogen, 21% oxygen, 0.9% argon, and 0.04% carbon dioxide. You do not need to memorize those numbers, but I think it's good to know that the air is actually mostly nitrogen. Nitrogen is a very inert gas, and so that's a good thing. But we need that oxygen in there too. And the plants appreciate the carbon dioxide. So sometimes we can treat a gas mixture as though it were one gas. Bless you. Because with gases, the size of the individual particles doesn't matter. And so we can measure the volume, the pressure, the temperature, etc., as if it were a pure substance. We can find the total number of particles or moles of particles using the ideal gas law. And this is because gas particles behave independently of each other. But sometimes we do need to think about what the individual gases are doing. So if we think of a single gas in a mixture, each gas is going to exert a pressure as if it were the only gas in the container. And so the pressure of a single gas is called the partial pressure. So if you have, say, 3 gases in a container, gas A, B, and C, gas A is exerting a pressure because its particles are running into the walls. Gas B is also exerting a pressure, and gas C is exerting a pressure. If you think of weighing something, maybe you're weighing a box of fruit, and it has apples and oranges and bananas in it. The total mass of fruit in the box is the sum of the masses of each one, right? The apples have a certain mass, the bananas have a certain mass, and the oranges, that was the other one. The oranges have a mass, and the total mass is all of them added together. It's a lot like that with pressures of gases. Each gas exerts its own pressure. The total pressure exerted by the mixture is the sum of the partial pressures of each of those gases. And this is known as Dalton's law of partial pressures. And this is the same Dalton, John Dalton of Dalton's atomic theory. We can calculate the pressure from a single gas, P, and my computer just quit on me. So we can calculate the pressure due to a single gas using the ideal gas law. And that would be nRT over V. So the pressure of the gas is directly proportional to the number of particles, the number of moles of gas. In this mixture, the temperature and the volume are going to be the same. So we say the total pressure is equal to the sum of the pressures of each gas. Well, the pressure from gas A is equal to the moles of A times RT over V. It's a rearrangement of the ideal gas law. The pressure from gas B is moles of gas times RT over V. The pressure from gas C, moles of C times RT over V. We can factor out this RT over V, and we see that the total pressure is equal to the total number of moles of gas times RT over V. So if we take the ratio of the pressure, the partial pressure of gas A divided by the total pressure, the pressure of gas A is the moles of gas A times RT over V. The total pressure is the total number of moles times RT over V. Those guys cancel out. The ratio of the partial pressure of gas A to the total pressure equals the number of moles of gas A to the number of total moles of gas. That's called a mole fraction. It's like a percentage, but we didn't multiply by 100. How many moles of A out of the total number of moles? If we multiplied by 100, that would be the mole percentage. This is the mole fraction, and we use the Greek letter chi to symbolize that fraction. So we can use this relationship to help us calculate the moles of gas. We can rearrange things here. The partial pressure of A over the total pressure of A equals the moles of A over the total moles of A. That's from up here. This moles of A over total moles of A is equal to chi A, the mole fraction of A. And we brought P total up over here, and so we get this relationship. Now, if all of that derivation stuff made sense to you, awesome. Give yourself a pat on the back. If you didn't follow that, that's okay. Just memorize this guy right down here. Okay, memorize him. The partial pressure of A equals the mole fraction of A times the total pressure. So let's say we had, I have to be a little careful when I make analogies with maths. Let's say we had a box. Let me draw a box. So here's a box. And let's see if I can do something. And we've got balls. These balls are all the same size, but they're different colors. Let's see, I did 6 of those, I'll do 3 of these. So let's say that each of these balls weighs 1 pound. How much does that whole box weigh then? It'd be 9 pounds. So there's 9 pounds because each ball is 1 pound. What fraction of the balls are blue? 1/3. It's 3 out of 9 balls is blue. So that fraction is 1/3. So what's the mass of the blue balls? It's 1/3 of the total mass, or 3 pounds. The mole fraction, 1/3, times the total mass gives us the mass of the blue balls. Now that may have helped a couple people, it may not have helped other people. If that didn't make sense, just forget about it. That's just an analogy. Okay? Sometimes my analogies are good and sometimes they really suck. So what can we do with that equation? The partial pressure of a component in a gas is its mole fraction multiplied by the total pressure. That's what that equation said. The partial pressure of a component, P of A, for gas A, equals the mole fraction of A times the total pressure. So if we know what the mole fraction is, then we can figure out what the partial pressure is. So thinking about dry air, nitrogen is 78% of air. Well, how do we change a percentage into a fraction? Divide by 100. So if 78% is nitrogen, then 0.78 out of 1 is nitrogen. So here's the mole fraction. So for nitrogen here, chi nitrogen is 78% divided by 100, which equals 0.78. So that's this guy right here. The total pressure of air at sea level is 1 atmosphere. So 0.78 times 1 atmosphere, that tells us that the pressure due to nitrogen is 0.78 atmospheres. Any questions? Let's do an example. To prevent the presence of air, noble gases are placed over highly reactive chemicals to act as inert blanketing gases. Highly reactive chemicals will react with things in the air. And so you can't just put them in a bottle and close the lid because just the air inside the bottle will cause them to react. So we need to cover them with something to prevent them to reacting. And so noble gases are often used because they don't react with anything. So a chemical engineer places a mixture of noble gases consisting of 5.5 grams of helium, 15 grams of neon, and 35 grams of krypton in a piston cylinder assembly at STP. Calculate the partial pressure of each gas. This is a question that you kind of have to think about a little bit. It doesn't just jump out at you, oh, I need to do this. Well, we've got STP, so maybe let's write down. So we've got STP. What does STP mean? Standard temperature and pressure. So the temperature is what? 0 Celsius or 273.15 Kelvin. And what's the pressure? 1 atmosphere. So pressure is 1 atmosphere. We have a mixture of gases. It's asking for partial pressure of each gas. So we should be thinking, well, the Dalton's law of partial pressure, those partial pressure laws. So let's see. The total pressure is going to be the sum of the pressures of each gas, the pressure of helium, plus the pressure of neon, plus the pressure of krypton. So I know that that's true. I also know that the pressure of the helium is going to equal the mole fraction of helium times the total pressure. So I'm just kind of writing down some stuff that I know and hoping that something's going to jump out at me and say, oh, hey, I could do this. Well, I've got masses of gases. Sounds like a Dr. Seuss book. Masses of gases. Do we do gas calculations with grams? No, we need moles, don't we? To figure out what the pressure of helium is, I need the mole fraction. So I'm going to have to figure out how many moles of each of these gases I have. So for helium, I've got 5.50 grams. And I can convert that to moles using the molar mass of helium. So 4.003 grams per mole. So 5.5 divided by 4.003. So that's 1.37. I hate rounding up that much, so I'm going to carry 3 digits this time to avoid that. That's how many moles of helium I have. And then I'm going to look at the neon. I've got 15 grams of neon. 20.18 is the molar mass. 1 mole. 20.18 grams. So 15 divided by 20.18. 0.743 moles of neon. And then I've got krypton. It always makes me think of Superman. 35.0 grams. And, 1 mole. Krypton is 83.80. So 35 divided by 83.8. 0.41766 moles of krypton. So I know that the total pressure, where's my pointer? Total pressure is the sum of all of these, but I don't know any of them, so this equation isn't going to help me out very much, because I know that they all add up to 1 atmosphere, but I don't know how it's divided up. So I need to use this second equation. So I can find the partial pressure of helium by finding the mole fraction of helium and multiplying by the the total pressure of the gas. Well, the mole fraction of helium, that's the moles of helium. So that's moles of helium divided by total number of moles. So moles of helium is the 1.37397 moles. And that's divided by the sum of all three of these. So 1.37397 plus 0.74331 plus 0.41766. Total number of moles is 2.53494 moles. That's total number of moles of gas. Where is the last significant digit in that number? What decimal place? The ones place, the tenths, the hundredths, the thousandths? We're adding. This has 2 decimal places, 3 and 3, and so our answer is going to have uncertainty in the second decimal place. There's a little review of sig figs for you. 2.53494 moles. So this mole fraction, 1.37397 divided by 2.53494. This mole fraction is 0.54201. There's no units on a fraction because the moles divided by moles, that cancels out. Your fractions have to be 1 or less. It can only be 1 if you only have a single gas. So if you end up with a mole fraction that's larger than 1, something went wrong. So if I take this number, that's the mole fraction for helium, and I bring it up here and plug it in, the mole fraction is 0.54201 times the total pressure. What's the total pressure? It's at STP. It's 1 atmosphere. So then the pressure from helium is 0.542 atmospheres. The partial pressure ends up being the same as the mole fraction because the total pressure is 1. If the total pressure was something else, then it would change. So how do we find the partial pressure for neon? The same way, we need the mole fraction, right? So the mole fraction for neon equals moles of neon, which we already calculated, 0.74331 moles, divided by the total number of moles, 2.53494. .74331 divided by 2.53494. The mole fraction is 0.29323. What's the partial pressure of neon? It's the mole fraction times the total pressure. Since the total pressure is 1 atmosphere, the partial pressure ends up being equal to the mole fraction. So for neon, the partial pressure of neon is 0.293 atmospheres. We need to do a similar thing for krypton. We could take this number and divide by the total and get the mole fraction. What's another way we could find the mole fraction? We could subtract. All these mole fractions have to add up to 1. So if I take 1 minus the mole fractions of the other two, so 1 minus 0.54201 minus 0.929323, I get 0.16476. Sorry, this is a horrible mess. That's the mole fraction. If I do it the other way, if I take 0.41766 and divide by 2.53494, I get 0.164761296. And because the total pressure is 1 atmosphere, when I take this mole fraction and multiply by the total pressure, 1 atmosphere, I end up with the partial pressure of krypton being equal to its mole fraction, 0.16, and for final answer, I'm going to round that up to 5. Any questions? This is the type of problem that's hard to do in your head without writing anything down. I wouldn't try to do this and just write down answers. I'd probably get it wrong. Any questions? Let's do another problem. A sample of hydrogen gas is mixed with water vapor. This is what we call a wet gas. The mixture has a total pressure of 755 torr, and the water vapor has a partial pressure of 24 torr. What amount in moles of hydrogen gas is contained in 1.55 liters of this mixture at 298 Kelvin? Well, let's write some of these things down. The total pressure, we'll call that P total, is 755 torr. The partial pressure of water is 24 torr. And then I've got a volume of 1.55 liters. I have a temperature of 298 Kelvin. And what are they asking me to find? Moles of hydrogen gas. So we have a mixture. We have two gases. What are they? Hydrogen and water. So this total pressure, Dalton's law of partial pressures tells us that that is the pressure of the hydrogen gas plus the partial pressure of the water. They told us what the partial pressure of the water was. Can we figure out what the pressure of just the hydrogen gas is? Yeah. The pressure of the hydrogen gas is going to equal the total pressure minus the pressure of the water. That's one of those things where the math is so simple that it freaks people out. It's got to be more complicated. Yeah, no, it doesn't. 755 minus 24 I believe that is 731 torr. Everybody okay with that? Two gases. They each exert part of the pressure. We don't need to go with moles here because in this total pressure equals the sum of the partial pressures, we know two of the values, we only have one unknown, and so we don't have to get more complicated than that. So now I've got the pressure of the hydrogen gas. It's important that we use the pressure of the hydrogen, because if we use the total pressure, we'll get the total number of moles of gas, both hydrogen and water. And it specifically asks for just the hydrogen. So I've got P, V, and T. I'm looking for N. I can use the ideal gas law. So I rearrange the ideal gas law. N equals PV over RT. So the pressure is in torr. What do we need to do? And I convert to atmospheres. So 731 divided by 760. I'm going to just write it in over here. 0.96184 atmospheres. And the volume of the gas is 1.55 liters. Our friend, 0.08206 liter atmospheres per mole Kelvin. And then the temperature is 298 Kelvin. Check the units. Kelvins cancel, atmospheres cancel, liters cancel. I end up with moles. So the moles of hydrogen is 0.96184 times 1.55 divided by 0.08206 divided by 298. 0.060966. That should have three significant figures, and so that's going to end up being 0.0610 moles. Any questions? There are so many possible problems that can be asked that the only way to be successful is to actually understand how to put these things together. You can't just memorize, okay, well, if it's this kind of a problem, I do this, and if it's this kind, I do that. In 3A, you can get along with that and get through the class, but you can't do that in 1A. You got to understand it. Deep sea diving. Partial pressures are really important in scuba diving. When a diver breathes compressed air, you have a higher gas pressure. And so you have an abnormally high partial pressure of oxygen, which leads to a higher concentration of oxygen in your body tissues. And this just points out again one of my soapbox things. Everything is toxic at some level. You know, water is essential for life, and yet water kills more people every year than any other substance. A lot of those deaths are due to drowning, but still, too much water will kill you, right? Too much oxygen can kill you as well. You get above 1.4, and you can get oxygen toxicity occurring. Hypoxia is when you get below about 0.1 atmospheres of oxygen. Oxygen starvation, suffocation. So you need to be in this zone in the middle. Well, if you're breathing compressed air, breathing air at a higher pressure, you're getting a higher concentration of oxygen, you're also getting a higher concentration of nitrogen. And that causes more nitrogen to get into your blood, and that can actually give effects that are similar to taking a narcotic. So it's sometimes called nitrogen narcosis or rapture of the deep. It has symptoms similar to alcohol intoxication. Is it good to be meters underwater and act like you're drunk? You could pass out, your judgment's impaired. It's not a good idea. So here at the surface, the total pressure of the air that you're breathing is 1 atmosphere, and so your nitrogen partial pressure is 0.78. 30 meters below the surface. In order to be able to breathe at all, the pressurized tank has to be 4 atmospheres. And so that gives you a partial pressure of nitrogen of 3.12 atmospheres. That's going to mess you up. There's something missing from my slides. So this example needs a little explaining. A diver breathes a heliox mixture with an oxygen mole fraction of 0.05. So one way to get around this is to use something besides compressed air. And so heliox is a mixture of helium and oxygen. Helium doesn't produce effects like that of nitrogen when you get a high concentration in your blood. It doesn't react with stuff, makes your voice high and squeaky, but you don't do a lot of talking underwater anyway. So a heliox mixture has a mole fraction of the oxygen of 0.05. So let's write that down. So the mole fraction of oxygen is 0.050. What must the total pressure be for the partial pressure of oxygen to be 0.21? So we want the partial pressure of oxygen to be 0.21 atmospheres. That's what our bodies are optimized for. That's the pressure of oxygen at atmospheric pressure. So we're good in that situation. What does the total pressure need to be? So we're looking for P total. Well, do we have an equation that relates those 3 things? How about this one? The partial pressure of a gas is equal to its mole fraction times the total pressure. Mole fraction, partial pressure, total pressure. We know 2 of them. We could calculate the 3rd. So I'm going to use this equation, and I'm just going to rearrange it and solve for PT. So the total pressure, if I want a partial pressure of oxygen to be 0.21, is going to be the partial pressure of oxygen divided by the mole fraction of oxygen. So the partial pressure is 0.21 atmospheres. Nope. Yeah, never mind. Sorry. Brain fart. Mole fraction is 0.05. So 0.21 divided by 0.05. That tells me that the total pressure on the tank, on this heliox mixture that the diver's breathing, needs to be 4.2 atmospheres. So at 4.2 atmospheres, he's going to be getting a good level of oxygen. Any questions? Now you come to the surface, and if you're trying to breathe this heliox mixture at the surface, you're not going to be getting enough oxygen. So a lot of times what they'll do is you'll have 2 tanks, and as you come up or go down, you adjust the ratio of the gases that you're breathing to avoid problems. How do you collect a gas? Gases are nice to work with in some respects, but difficult to work with in other respects. Liquids are great. You put them in a beaker, and they sit in the beaker for the most part. Solids, you can put them in a container, and they just sit there. Gases, unless you keep a tight lid on them, they just float all over the place. How do you collect a gas? A lot of times we do this by having the gas displace water from a container. I think I have a picture. Nope, I don't. I'll have to draw one. Oh, this will be ugly. Okay, so one way we can do this is we can have some sort of a container full of water, and then we can put an inverted test tube full of water in there. Oh, my eraser's too big. Okay, so this test tube is full of water. As long as the test tube is less than 32 feet tall, this works just fine. And then over here, I have a test tube where I'm reacting something and it's giving off a gas, and I want to collect the gas. So what I can do is I can put a stopper in this, and I can run a tube through a little hole in the stopper, and it'll come out down here under this other container. As the gas is pushed out of this container, this test tube, it's going to go through the tube, and it's going to bubble up, and it's going to displace the water. And we'll see that the water level goes down as this gas begins to fill up the inverted container. Does that make sense? You could try this at home with hold a drinking glass up and stick a straw under there and blow. As you blow air under that inverted glass, the air will go up and it'll get trapped and it can't leave. And so this is how we can collect a gas. This is called collecting a gas over water. So what we have here in this space is the gas we're interested in, but we also have some water vapor because water evaporates. It's not considered really a volatile liquid, but it does evaporate it, and it is a measurable amount. Well, the partial pressure of the water vapor in here is interesting. It depends only on the temperature of the water. So if we know what temperature this water is, we can actually look up the vapor pressure of water, the partial pressure of water, in a table, and then we can figure out what the pressure of the other gas is. So this is an example of one of those tables. This one is not really specific. Others divide it up, every degree or tenth of a degree. But if we knew that our water was 25 degrees, then we could say that the vapor pressure, the partial pressure of the water above it, was 23.78 millimeters of mercury. If we know the total pressure, we can subtract the vapor pressure of the water and get the pressure of the gas that we're interested in. Any questions? There's my picture. I should have the picture before. Isn't that much nicer? So here's zinc reacting with hydrochloric acid, generates hydrogen gas. It goes through the stopper. It builds up pressure and it's trying to get out. So we say, well, you can get out, but you can only come this way, and we direct it underneath this inverted beaker. And as it comes up, it displaces the water, pushes the water out. And so we have our hydrogen molecules in here, but we also have some water molecules in here. So we have a mixture of gases. Any questions? How do you get the tube inside down here? Well, this is a stopper that has a hole in it. And so you have glass tubing that sticks into the hole. And that's a lot easier said than done. It has to be just the right size, and because it's really easy to break that tubing, that glass tubing, when you're sticking it in, which results in nasty cuts on your hand, right? So you got to be real careful with stuff like that. But it can definitely be done. So that's how we do that. Any other questions? This is not a fancy setup, right? It's beakers, test tubes, dishes, water, right? Glass tubing, nothing super fancy. Of course, you can make much fancier things, but this, pretty much anybody could put together in a general chemistry lab if they needed to. So let's do an example of the type of calculation we might need to do. A sample of acetylene is collected over water. So whenever you see collected over water, you should say, we're going to have to use Dalton's law of partial pressures. There's water vapor and the gas I'm interested in. So the total gas pressure is 738 torr. The volume is 523 milliliters. At the temperature of the gas, 23 degrees Celsius, the vapor pressure of water is 21 torr. How many grams of acetylene are collected? Well, let's collect some information here. So I've got total gas pressure. So the total pressure is 738 torr. It tells me that the volume of the gas is 523 milliliters. The temperature is 23 degrees Celsius. The vapor pressure of water, that's the partial pressure. Vapor pressure is just another word for partial pressure, is 21 torr. So I've got all of this information, but I'm trying to get grams of acetylene. Mass is not a number that we can calculate using gas laws, but we can calculate moles. And they gave us the formula for acetylene, and so if we find moles, then we can just convert that to grams. So what we're looking for first is moles of gas. I have to realize that my total pressure is the gas I'm interested in, the acetylene, the C2H2, plus the water vapor. And I need to use the pressure of just the gas I'm interested in, otherwise I'm going to get the total number of moles of gas, and I don't care about the water. So the partial pressure of the acetylene, which does not start with H, C2H2, is going to be the total pressure, 738, minus the pressure of the water vapor. 738 minus 21. I should do that in my head, but I'm not going to. 717. And that's torr. I'm just going to convert that to atmospheres right now. I'm going to divide by 760, and that's 0.94342 atmospheres. To find moles of gas, N equals what? PV over RT. Just a rearrangement of PV equals nRT. I need the pressure of the gas, 0.94342 atmospheres. I need the volume of the gas. Is milliliters going to be a good unit? No, I need liters. So that's 0.523 liters. And then I've got the gas constant, 0.08206 liter atmospheres per mole Kelvin. That's one of those things, we end up using that so often that you don't even really need to pay attention to memorizing it. And then temperature. Well, I can't use Celsius, so plus 273.15. That's what, 296.15 Kelvin? Yeah. Units, atmospheres, atmospheres, liters, liters, Kelvin, Kelvin, that's okay. 0.94342 times 0.523 divided by 0.08206 divided by 296.15 equals. So that's how many moles of acetylene I've got. I'm going to come up to the top because I ran out of space. 0.02203 moles of C2H2. How do I get that into grams? I need the molar mass. So the molar mass is 2 times 12.01 plus 2 times 1.008. 26. 26.036. that ends up being 0.529 grams of acetylene. Any questions? Here's another one. Common way to make hydrogen gas in the lab is to place a metal such as zinc in hydrochloric acid. The hydrochloric acid reacts with the metal, producing hydrogen gas, which is then collected over water. Suppose a student carries out this reaction and collects a total of 154.4 milliliters of gas at a pressure of 742 millimeters of mercury and a temperature of 25 degrees Celsius. What mass of hydrogen gas in milligrams does the student collect? So many words. Well, let's identify what the numbers mean. I've got a volume of 154.4 milliliters. I have a pressure of 742 millimeters of mercury, and I have a temperature of 25 degrees Celsius. Can I take these numbers and just plug them into the ideal gas law? No, not quite. Why? I've got hydrogen gas, but I also have what? I've got water. Because collected over water. If it's collected over water, it's a mixture. So this pressure that I'm given is the total pressure. I need to find out what the pressure of the hydrogen is. How am I going to do that? I need the pressure of the water. So I'm going to have to look this up. This one doesn't give me all the information I need. Now, you do not need to memorize this table. If you need this information on an exam, I'll give it to you. So at 25 degrees, that's the temperature, it's 23.78 millimeters of mercury. 23.78 millimeters of mercury. That is the partial pressure of the water. So then my pressure of hydrogen equals the total pressure minus the water. 742 minus 23.78.
Can I ask you real quickly?
Uh-huh.
The last one you added the pressure of the water. What's the difference between those two? Because you took the pressure total and then you added the pressure of the water.
I think they subtracted.
Well, I was confused by that because I started with the adding. Oh, okay. I just read wrong. Sorry.
Yeah, because that wouldn't make sense.
Yeah, okay.
Which, you know, I've done things like that, but hopefully I didn't do it this time. Okay, so when I subtract this, I get 718.22. The units are millimeters of mercury. I'm keeping track of significant figures, and so my uncertainty lies in the ones place there. So there's my pressure of hydrogen. And it's asking for mass of hydrogen gas. We're going to find the moles first and then convert it to mass using the molar mass. So we've done a lot of these problems now. We need to convert the pressure to atmospheres, and that's done by dividing by 760. So this is equal to 0.945026 atmospheres. So that's the pressure of hydrogen. My volume is going to be 0.1544 liters, and the temperature is going to be 298.1415 Kelvin. So we've done those conversions a zillion times now. Number of moles is PV over RT. So repetitive. 0.1544 0.544 liters times 0.945, 0.026 atmospheres, divided by 0.08206 liter atmospheres per mole Kelvin. And then I need the temperature down there, 298.15 Kelvin. So number of moles, 0.1544 times 0.9450. It's not a zero. We're up to 6. Divided by 0.08206 divided by 298.15. N equals 0.0059638 moles. I need to convert to grams. Grams per mole. What's the mass of 1 mole of hydrogen gas? 2.016, because it's diatomic. So that'll get me grams, and then I need milligrams. So I'm going to toss that in here. Grams on the bottom, milligrams on top. Grams cancel out. So I've got my moles times 2.016 divided by 1 EE negative 3. 3 sig figs, 12.0 milligrams of hydrogen gas. Any questions? We'll save this for Wednesday.